好，那我们接下来就欢迎蓝天。
可以看得到吗？Okay. So yeah, as the host introduced, I'm a PhD candidate in Ruhr-Universität Bochum and work in ITM Center. In this center, we have people working at uh, electronic scale simulation and also atomic scale simulation, and also people using simulation to study microstructure. I personally is involved in atomic scale simulation. And today I want to talk about ferroelectrics and their application on solid state cooling. And I learned from the survey that not some of you have only heard of this for the first time. So I'm going to give an introduction of this material, and then I will move on to my currently close project related to the application on solid state cooling. So yeah, so what is ferroelectric materials? We can have definition coming from the symmetry of the lattice, and we can also have the definition coming from the properties, and this is the definition I'm going to use today. So all the material that have reorientable spontaneous polarization are considered ferroelectric materials. As we know that if we put a dielectric on the electric field, then electric field will induce polarization inside the material. But polarization is the total electric dipole moment per volume, and this is the electrodipole moment, just to bring everyone to the same page. But for ferroelectric, this polarization is spontaneous. That would mean that even without an electric field, the material still exhibits this polarization. Furthermore, for the material to be considered as ferroelectric, the polarization needs to be reorientable. So that would mean that there are several states that is possible for the polarization. So you can think of it like the polarization can point into 100 direction, but it can also point to 010 direction. And in this case, it has to be reorientable. That means from 100 to 010 should be possible for the material to be considered ferroelectrics. So yeah, I just said that the definition for ferroelectrics is that it has to be reorientable spontaneous polarization. And these properties make ferroelectric a candidate for a memory device. So it's actually quite straightforward. For a memory cell, we wanted to be able to, we want to store bit value, which are 1 and 0 inside our memory cell. And for ferroelectric, we can say, okay, if now the material has polarization pointing to plus X direction, then let's call it bit value equal to 1. And then if it's point to negative X direction, then we say this is bit value equal to 0. In this way, we can store data. And all ferroelectrics, they are paraelectric material. That would mean that if this ferroelectric material experience thermal gradient, then it will generate electric field. And this make it a good candidate for infrared sensor and also solid state cooling. One of the property I will talk more later. As we know that paraelectrics, they are all piezoelectric. That would mean that the material will generate electric field when it's under mechanical field, so stress or strain. This make ferroelectric a material for underwater sonar and sound generators. Of course, all of them are dielectrics. Therefore, one can also use ferroelectric for capacitors. So these are, so we already see that ferroelectrics interact with electric, thermal, and mechanical fields, and therefore provide a broad playground for us and also provide diverse application. Now, let's take a step back and see how these can happen. So from now on, I'm going to concentrate on this barium titanate. This is a ferroelectric material with perovskite oxide structure. At high temperature, it will look like this. So it's in the central symmetric structure where no dipole moment can be found. And in this state, we say that it's in its paraelectric phase. Now with the stimuli, for example, electric field, we can move the titanium that is in the center off-centered. In this way, a dipole moment is generated. And whenever the material have dipole moment, then it means that it is in its ferroelectric phase. For barren titanate, there are 7 possible ferroelectric phases. As shown in the figure, if the polarization point to 1 or 0 direction, then it's in its tetragonal phase. If it point to 110, then it's orthorhombic phase. If it point to 110, then it's rhombohedral phase. It can also point to other direction and, for example, monoclinic phase or triclinic phase. Under zero field, we only observe 3 out of 7 of the ferroelectric phase. So at the highest temperature, we have paraelectric phase, which is this phase shown here. And then we're having tetragonal phase, orthorhombic phase, and rhombohedral phase. We can take the polarization as autoparameters, and this, what I'm showing you, is the phase diagram. This material undergoes transition at different temperature, depends on its thermal history. So the phase diagram in blue, so the curve in blue tell you the phase diagram for a cooled sample and the red one for a heated sample. You can see that the gray region marks the coexistence range and the temperature are called thermal hysteresis. You can also see that at the transition, the polarization changed abruptly. That would mean that this is actually a first order phase transition. And how does this transition happen? To answer this question, we can look into the Landau theory. And this is the energy landscape. So y-axis shows the energy and the x-axis shows the autoparameter, which is the polarization for ferroelectric materials. At the highest temperature, there's only one possible state. Only the state with polarization equal to 0 is stable, and this state is paraelectric phase. When the temperature reduces, at some point, this ferroelectric phase where polarization is finite will also have the same energy as the paraelectric phase. And then with the even lower temperature, this ferroelectric phase will be the only state that is stable for the material. This is how, by lowering the temperature, the system transits from paraelectric phase to ferroelectric phase. And you see here, there is an energy barrier. This is a unique characteristic for first order structural transition, and it also is the reason for thermal hysteresis. Now, in the very beginning, I told you that ferroelectric material are the material that have reorientable spontaneous polarization. So that would mean that, for example, the material should be able to go from the orange state to the red state or the other way around. And how does that happen? Here I'm showing you the field hysteresis, and let's say we apply a very strong electric field along upward direction so that the system go to the saturation state with one domain pointing upward. Now we reduce the electric field, and then at some point we totally remove our electric field. At that point, they will have a remaining polarization, and it's called remnant polarization. And then we started to apply electric field to the downward direction. And then more other domain, especially the downward pointing domain, will be favorable and then started to grow. This electric field is called coercive field. If we continue to strengthen the electric field in the downward direction, in the end, we will reach another saturation point where the system consists only domain pointing downward. So this is the orange state. And now I just show you how the system can go from red state to orange state. And it goes from polarization pointing upward to downward. This is what we call polarization switching. And this is the very important properties for ferroelectric materials. So now I have introduced you what is ferroelectrics and its application and the mechanism that make all this property possible. Now we're going to move on to the solid-state cooling technology based on electrocaloric effect. So what is electrocaloric effect? Caloric effect tells you that there is a temperature change, and electro indicate that this is an electrically driven phenomenon. We can quantify it as the temperature change caused by the application or removal of an electric field under adiabatic condition. So what is this, and what advantage can we, why is it better than other solid state cooling technology or other cooling technology? So first of all, it's in solid state. That means we don't need any cooling agent, and also there's no moving part. Therefore, it requires low maintenance, and it will also produce the noise is also it can also be quiet because it doesn't need a compressor like our conventional refrigerator. It can be environmental friendly because we don't have to worry about the leakage of the environmental harmful cooling agent. It can also be made into very small scale. Therefore, we can imagine that we can have this for on-chip cooling for battery, and the stimuli, which is the electric field, is easily obtainable. So there are other prototypes that we can think of for this electrocaloric-based solid-state cooling technology. For example, we can embed it into your chair, and then you can have a cool chair that cools you. Of course, we can also use it to cool down fluid medium and just put the EC material here, electrocaloric material here, and let the fluid go through it. Here I'm showing you the cooling cycle for the conventional refrigerator, which make use of liquid vapor phase transition, just shown here so that you can have some impression. And then this is the cooling cycle for the electrocaloric effect-based solid-state cooling technology, which make use of the dipolar phase transition. So at the very beginning, dipolar point to a random dipoles moments point to random directions, and now we apply an electric field which force the dipole to align. And when they align, the dipole configuration entropy is reduced. But since we operate in this in adiabatic condition where total entropy should be conserved, lattice vibrational entropy will increase, and thus the temperature increase. Now we release the heat, and the system is back to the original temperature, but this time with polar dipole moment all being aligned. Now we remove the field, and the dipole configuration entropy increase. Therefore, lattice vibrational entropy should reduce. In this way, the temperature is reduced. What I just showed you and explained is the conventional ECE. For conventional ECE, when we remove the electric field, temperature reduce. There are another kind of ECE. So at some condition, we will observe inverse ECE. That would mean that when we remove the electric field, temperature actually are going to be increasing. And this is because at those conditions, the reallocation of the entropy is different than what it is for conventional ECE. We can cascade this EC cycle and in the end obtain a larger temperature change. So this is for the introduction for the solid-state cooling technology. Of course, there are challenges. Here, I'm only listing a few that are related to my study. So what we observe is that this electrocaloric effect is large at phase transition, and it's largest at the para-ferroelectric phase transition, which is the highest temperature transition, which are normally above room temperature. However, for our daily cooling needs, we would like it to be near room temperature, or at least a little bit lower than the room temperature. Therefore, this is one challenge. The second challenge is that as I showed you in the beginning, we see that ferroelectric material exhibit first order structural phase transition, and that means that would lead to very narrow temperature window for large ECE. However, we of course will want this temperature window to be broader. The third challenge is that for application, we use ceramics and not single domain crystal. And it is observed that the total net ECE effect observed in ceramic is much smaller than it is in single crystal. The fourth challenge is that ECE can be irreversible. And what does that mean? So the first time when we vary the field, apply or remove the electric field, the temperature change is huge. But the second time when we do so, it's very small, and it's just remained to be so small for the field cycling operation. And this is of course not what we want. There are several ways people are trying several ways to try to cope with these challenges. For example, you can try to change the mechanical mechanical condition and apply a biaxial strain, for example. This is a strain you will the material will naturally experience in film when they grow it on a substrate that have lattice misfit. So as you can see here, if we apply, if there is biaxial strain, if the material experienced biaxial strain, then the transition temperature can be tuned. For example, here they experience compressive strain, and the transition temperature between paraelectric phase and ferroelectric phase increase. Well, and in between the other phase also change. So biaxial strain can change the transition temperature, and therefore change the temperature where large ECE can be observed. Now, people can also change the chemical composition, and in this way, you can see that the transition temperature can also be changed. Also, the phase sequence can also be changed. Beside this, they can also try to do something with the operation parameter. And this study shows that with a stronger electric field or a larger field variation range, the magnitude of the ECE can be changed. So as you see here, with a stronger electric field and a larger variation range, the ECE value is increased. The magnitude of the ECE is increased, and also the temperature range for large ECE is broadened. Beside the strain of the electric field, one can of course also consider changing the direction of the electric field. And this study shows the ECE in different high symmetric direction, under electric field in high symmetric direction. It shows that the magnitude of the ECE and the temperature window, and also the type of the ECE can be tuned by the electric field direction. So this is exactly what I mean by inverse ECE. When they remove the electric field, the temperature increase. This is inverse ECE. And when they remove the electric field and temperature decrease, then this is conventional ECE. And these are anisotropic properties to electric field direction. So the work that I'm going to introduce you later is actually motivated by this work because this is a simulation work, and they only check the high symmetric direction. And so we were thinking, what if now we apply electric field in low symmetric direction? How will this modify the phase diagram? How will this modify the electric caloric effect? And would it be possible by changing the direction of the electric field? Would it be possible to solve these challenges by changing the direction of the electric field? So we also do simulation work, and we use this Furon package, which is a coarse-grained molecular dynamic package specialized for ferroelectric perovskite oxide structure. In this scheme, we don't see atomic detail, but we see for each unit cell, we see only one dipole moment. And in this way, the degrees of freedom for each unit cell is reduced to only 3. So XYZ component for dipole moment. The energy of the system is described by this affected Hamiltonian, and As you can see in the formulation, we have the kinetic energy of dipole, we have dipole-dipole long-range interaction, elastic energy, and the coupling between strain and dipole moment. Because for ferroelectric material, dipole moment and strain, they are important feature, and they influence the energy. And here, all the necessary terms that are needed for ferroelectric motions are considered. So we can measure the electric caloric effect as this. So we first thermalize the system at the condition that we want, so temperature and the electric field direction. And then we gradually remove the electric field, and then we thermalize it further. And then the ECE can be qualified by the temperature change between before and after the field removal. So that exactly this difference. We sampled not only the high symmetric direction, but also the low symmetric direction that lies on these colored planes, and also those that have even lower symmetry that are bounded by this region, so the green ones. We found that by applying electric field that is not parallel to the spontaneous polarization, the electric field is going to homogeneously rotate the total polarization. So this black arrow shows you the direction of the electric field, and the red ellipse shows the polarization distribution in this case. So we see that while we rotate the electric field, the polarization are going to be rotate. It will not be exactly in the same direction like as the electric field, but it will be rotate and homogeneously. This is not the case for all ferroelectric materials. For example, for a lead titanate, when the electric field rotate to 110 direction, we see that it decomposes into two tetragonal domains. Actually looks like this. So we will observe tetragonal domain separated by 90-degree domain wall, uncharged domain wall. But for barren titanate, it will polarization will be rotate homogeneously. This is one thing that we learned. And here I'm showing you that the field direction dependence of the transition temperature. So in the x-axis, I show you the direction of the applied electric field, and y-axis is the temperature. We know that barren titanate exhibits 3 transitions. So you see 3 pairs of the horizontal line and the curves. The horizontal line shows you the transition temperature in zero field. Red for heated sample, blue for cool sample. Thick curve shows you the transition temperature under an electric field. I also show you from the very beginning that barren titanate undergoes transition from cubic phase to tetragonal to orthorhombic to rhombohedral. So I'm just marking it here. So just mark there. As the electric field will rotate the polarization, of course, the phase has been changed. And these are the actual phases that appeared in the simulation. What we can see is, for example, if we apply electric field in one or all direction, then this tetragonal phase has been enlarged, and the transition temperature between paraelectric phase to ferroelectric phase is increased. And now if we rotate the electric field to 110 direction, we see that tetragonal phase started to the range for tetragonal phase reduce, and the range for orthorhombic phase increase. At that time, we were thinking, how can we understand this field direction dependence of transition temperature? And we're thinking that, well, let's just try and see if it we think it, of course, has something to do with the coupling between the electric field and polarization. And we started from checking this term, E dot delta P. We see that it has a relatively okay, and it can quantitatively estimate quite well the change of the transition temperature. So we can see that at the highest transition, it goes first down, and then further down, and then up again. And this is exactly what we see in the simulation. But what worth noticing is that the delta P that we use here is the polarization difference at zero field. So we didn't consider the polarization that is induced by the electric field. And we also didn't take any domain structure into consideration. But it still already shows a qualitatively good estimate. So we're thinking this probably indicate that this field direction dependence is a phase-dependent properties and not a material-dependent one. So we went on to check another material, lead titanate, and lead titanate undergoes transition between cubic phase and tetragonal phase in zero field. So it corresponds to the first transition in barren titanate. And be careful, the axis is different, but we can see that if we move from 110 direction to 111 direction, transition is reduced, and then it increased when we rotate the electric field from 110 to 100, and then it reduced again. So it shows the same phase. What's quite surprising is that for lead titanate, as I just showed you, it has multi-domain. So it seems like this result is telling us that regardless of the domain wall pattern, regardless of the number of domain wall, regardless of the induced polarization caused by the electric field, the field dependence of the transition temperature will just look like this and is phase dependent. Now, we also check the thermal hysteresis. Thermal hysteresis is basically the difference between the heated and the cooled, the transition of heated and cooled sample. So the difference between the red and blue curves. I'm showing you here on the right-hand side, only the transition for the second and the third, and only the second and third transitions. So what we learn is, in general, under an electric field, the thermal hysteresis is reduced. And it's the largest under an electric field along the 100 direction. And now it can be reduced if we use a low symmetric direction. For example, it's greatly reduced if we use a direct low symmetric direction on O -1,1 plane. It will be minimum if the transition become isostructural. For example, here the transition is between two monoclinic C phase, or even here it's between triclinic phase. Here you can see that thermal hysteresis is almost zero. Now I want to show you how electrocaloric effect is modified by the direction of the electric field. And this is quite informative figures, but we have already walked through the part for transition temperature and also for the thermal hysteresis. Now I just added one more information. So the normalized delta T is how we quantify the electrocaloric effect, and the magnitude of it is represented by the color of the circles. So the conventional EC are marked with red or orange, and the inverse EC are marked as blue. And if it's with smaller magnitude, then it will be green, for example, like here. What we see is that we can observe large conventional ECE for a cooled sample at temperature between heated zero field heating transition temperature and field cooling transition temperature. So exactly this region here, and also this region here, for example. And we can observe large inverse ECE between the cooling transition temperature on the field and without field. So here, for example, and here. And the EC is largest on the electric field along the 100 direction, in this direction. You cannot see it here now, but I will show you with another way of visualization later. we see that at the paraelectric ferroelectric phase, the ECE remain conventional, no matter in which direction the electric field is pointing to. But for the two lower temperature ferroelectric to ferroelectric transitions, the type of the ECE depends on the field direction. So for example, for the second transition, we observe conventional ECE if we have electric field pointing on this -110 plane. But we're going to observe inverse ECE if we have electric field pointing to 100 direction. We also see that sometimes ECE is quite sensitive to the field direction. For example, here, if we just rotate the electric field by 8 degrees, we're going to observe weak temperature change and no longer this strong inverse ECE. Also the same case for the ECE here. Whereas for this here and this inverse ECE here, they seems quite robust to the electric field direction. Now the same data, but I plotted as a temperature, as a function of temperature. Now you can clearly see that the largest ECE occurs at under electric field along 100 direction, the black curves here and also here. We also see that how temperature window depends on the transition temperature. So this is the temperature window that I'm talking about, and this is actually bounded by the transition temperature in field and transition temperature in without field. So the gray regions are the coexistence range in zero field. It's actually clear here if we look at this region. So the blue curve, the temperature window for a large ECE is bounded by this triangle. So the transition temperature in field and the gray region. And for electric field pointing to 110 direction, the temperature window is larger and it's bounded by the transition temperature. We also see that for, oh, I forgot to say that this is the ECE for the first transition, so the paraelectric to ferroelectric transition, and the B figure corresponds to the ferroelectric and ferroelectric transition. So exactly this second one. We see that at the first transition, so paraelectric to ferroelectric transition, the ECE appear like a broad peak. But at the ferroelectric to ferroelectric transition, the ECE appear more like a plateau and not a peak. And this is because at this highest temperature transition, the transition is almost driven to be more second ordered, and therefore it has another contribution to the ECE. Whereas for the ferroelectric to ferroelectric transition, ECE is caused by only the contribution only come from the first order because the transition stay more or less still first order.
Hi, Lan-Tien.
Yeah.
Sorry. Can I ask a few clarification questions before we go on?
Yes.
Yeah. Could you go back one slide?
Yeah.
So I just want to understand how to read your plot here.
Yeah.
So I am assuming that the x-axis is the field, the electric field direction.
Yes.
And I should so for example on the 100, I should starting from high temperature, I should expect a tetragonal phase, MC phase, MMA.
Exactly.
Okay, but how do I understand, like if we go from tetragonal to tetragonal, why is there a phase transition?
Oh, so here you're observing isostructural transition. For example, this is also the case for here you're observing triclinic to triclinic to triclinic to triclinic. That means you mean how do we know that there is a transition, right?
Yes, and I also don't understand what does it mean by when you have a two identical phase, identical like a crystal structure. Why is there a phase transition?
So it's it is correct that the crystal have the same symmetry, but the magnitude of the dipole moment or the magnitude of the polarization are different. So for example, just for a case, for example, we can have tetragonal with 100, okay, 30, 0, 0. This is tetragonal phase, but it can also be 40, 0, 0. It's also tetragonal phase.
Okay, and you are saying the magnitude of polarization, there's a jump.
Yes.
At some certain temperature.
At this temperature for this
okay
case.
At that temperature, yeah, right. Okay, I see.
Yes. Since you asked, there is another details. Actually here, the electric field that we apply is actually quite strong. Actually strong enough to drive the transition to second order. So here if you look at the polarization curve, it will be the jump will be not that abrupt anymore.
Oh, okay.
Yeah.
And how strong is your electric field? How does it compare to coercive field?
Okay, it's stronger than that. We're using 100 kilovolt per centimeter. This is for our simulation and is very large if we're thinking an experimental setup. But we want to study a trend and not exactly the magnitude and the value.
Okay, but do you know the number for the I don't remember the number for the coercive field. Like I just want to get the magnitude. It's like 1 kilovolt per centimeter.
For simulation, it will be much larger than it is in experiment. But right now, I also don't have the number in mind.
Okay.
Yeah, but it's larger than that.
It's larger than that. Okay.
Yeah.
I see. And what are all these dots? Like the orange and yellow dots.
Yes. So the color of the dots represent the magnitude of the ECE. So if you see red one, then it would be conventional ECE, and if you see blue or green, then it's inverse ECE. And they are marked at the temperature and the electric field that is the system is in.
I see. So I should read it as like around the phase transition, there's a range that you can observe ECE, and around inside that range, you can give a value to the ECE depending on this color bar. Is that how I understand
it? Yeah. So you can observe ECE in at all conditions, but just sometimes they are stronger and sometimes they are weaker. And the yellow one means it's very weak. So
okay.
So exactly between these two between this temperature range. So basically here you have large ECE, large conventional one, and between the field cooling transition temperature and the zero field cooling transition temperature, we're going to observe an inverse ECE.
I see.
Yeah.
Okay. Yeah. Okay. So now I think I understand how to read your plot. Okay. Thank you.
Thank you for asking.
Yeah.
So that I can have some chance to explain more. So now we learned how electric field influence the transition temperature. I presented to you how electric field direction influence the transition temperature, thermal hysteresis, and electrocaloric effect. So how can we use this knowledge to cope with the challenges that I just showed you? Basically, we want a large ECE near room temperature with broad temperature window. And with this diagram, we can say that you would like to apply the electric field on negative 110 direction. So here you can have large conventional ECE near room temperature. Now you will ask, 200 Kelvin is not room temperature. Well, that's true. But that is because our simulation systematically estimate the transition temperature. So there are experimental work they record the ECE on the electric field pointing to 110 direction, and they found that the transition temperature, their experimental work studied the transition temperature on the electric field along 110 direction, and they found that the transition temperature happened at room temperature. So it's fair to say that this region will all be at room temperature, and also here. So basically, if you apply electric field on this negative 110 plane or around 110 direction, then you will have a large EC near room temperature. And the second challenge was the ceramics. So with this figure, we can also suggest that if you want strong, large conventional EC, you would like to texture your ceramic to this negative 110 plane so you can observe this, and you will not expect a strong ECE near this temperature range, because here you have weak ECE, conventional ECE, and inverse ECE, and they're going to cancel each other. So you will not expect large ECE here. You could expect large inverse ECE at this low temperature if you have textured ceramics to 001 plane. And the third challenge is regarding the reversibility. So reversibility is related to the thermohysteresis. The smaller the thermohysteresis, the better the reversibility. And with this diagram, we can suggest that go for a low symmetric direction. It will give you better reversibility, especially those that have really low symmetry. So with all this, you probably want to, this range is probably a good option if you want large conventional EC near room temperature with good reversibility. So that's all for my talk today, and I'm happy to take any questions.
OK， 那让我们谢谢蓝天。那大家可以打开麦克风给蓝天一个掌声，或者是用下面那个 reactions 给他一个掌声。那在录影还留着的时候，有没有人想要问问题呢？可以举手，或者是直接发问也可以。
Hi.
Hi,
Can you hear me?
Hi.
Yeah. Nice talk. So can you go back to your slide number 10 or 11? Like 10, I guess.
Yeah.
Yeah, I have a quick because your model you do the atomic simulation. So basically all the like all the unit cells just simulated as a single dipole moment. So I assume that you don't have this electronic level information, but I still want to ask, like, what is the fundamental difference between boron and lead?
Okay.
Because of a d orbital, I guess. I don't know.
Okay. I cannot explain it from the orbital wise. I mean, yes, they have difference there, but I can tell you from what I read from the literature, it is also observed. First of all, it's observed in experiment that lead titanate have this kind of multi-domain structure, and the other simulation found also this kind of structure when they're doing different simulation, and they suggest that this is because lead titanate has a stronger polarization strain coupling, and therefore it will not allow the polarization to rotate that much. Instead, it would like to just decompose into multi-domain.
So you're saying strain coupling, that is the eta term in your Hamiltonian, right?
Yeah, that's
a homogeneous strain.
So this
yeah.
These two.
I see. And how do you know how to model this strain tensor in this Cosgram code?
So this U is like dipole moment, and this W is a local strain. So they are both considered as a degree of freedom in the simulation. And how you get the value of the strain, they for example, they optimize the energy of the this elastic homogeneous potential and coupling between homogeneous strain and the polarization. They minimize the sum of these two, and they get the homogeneous strain. Is this what you're asking?
Kind of, but yeah. So, but what you're saying is basically because lead and bromide, they have different electron strain coupling. So, like the term you are pointing to. So, when you minimize the energy, you get different behaviors. Is that what you're saying?
Well, when the program minimize this, they get the value of the strain. As of and the reason that the lead titanate has this multi-dimensional structure is because that structure if lead let me go here. Okay, so for lead titanate, this structure has a lower energy than this structure, so it would like to stay here.
I see. Okay, thank you.
Thank you for asking.
Yeah, I have a follow-up question. So I thought the barium titanate also has a multi-domain experimentally.
Yes.
I think people observe that, right? And
yes.
What's the difference between multi-domain in barium titanate and the lead titanate?
Well, it have to see if they if they show multi-domain in the same condition. For example, actually here I show you the phase diagram for the strain temperature phase diagram for barium titanate, and here actually they see in simulation a multi-domain structure, and this is because the condition is different. So and for experiment, there are even more things that need to be considered. For example, in experiment, they could have defect, and they also maybe it's not. I don't know if it's a single crystal. Otherwise, you have to consider grain boundaries and so on.
Okay, that's right. Oh, okay. Yeah.
But with this data, I just want to show you that. Why is it? With that, I just want to show you that if we just consider the effect of the direction of the electric field, then for barium titanate, there will be a homogeneous rotation.
So I'm curious, so for all your simulation, does it mean that for all your simulation, your barium titanate is in a single crystal domain?
It's in single domain structure.
Oh, it's in single, okay. I see. But usually when you use it as a what is it called, the cooling material, it's in a ceramic form.
Yeah, they normally use ceramics because the cost is lower.
Okay. I see. Oh, okay.
It's easier to produce and therefore lower cost.
Right. But so how does your result translate to like real case? Will there be any difference?
So so we can look at this figure. For ceramic, we can think of it like we have to consider the grain boundaries and also the little grains that point into little grains that experience electric field in different directions. So my work concerned mainly the latter. And of course, we didn't consider grain boundary, but at least we consider the latter. And with this, we can infer from this phase diagram that what we can observe. For example, at this temperature range, we would expect really small temperature change, whereas at least we can expect a large temperature change for conventional ECE. This kind of information. Yeah.
I see. So let me rephrase. So basically, you think the ceramic is basically an average of your like domains with different orientation. They align to your electric field differently, and then you basically just average their effect. And then but you think that's your answer in the ceramics?
It will not be exactly because we didn't consider the effect of grain boundary. But yes, for each grain, we are expecting this kind of difference, because if you consider each grain, then there's each single domain grain, let's say, then you when you apply electric field on the adiabatic condition, then they will show a temperature change. And of course, one also need to consider the heat transfer between each grain and so on. But we think this effect will we can try to infer some information from single domain system.
I see. Interesting. Okay. So I have a question. So I'm an experimentalist. Is there a way you can explain this field dependent phase transition temperature change by Landau theory?
I see. So in Landau theory, we can include the field coupling term. Actually, that is how we first get the idea of using the E dot delta P term. Normally in the Landau theory, for first order, you need to consider up to the sixth order in the polynomial, and then you will add this E dot delta P term there as when you want to consider a system under electric field. So you ask if we can see this in Landau theory.
Yeah, can we draw like a so something like this, and then we add electric field. One side will become lower, the other side will become higher, right?
Yeah, exactly.
Okay, and then how does that explain? Can this explain the temperature variation in the phase transition?
So, for Landau theory, then we can think of it like this middle term is cubic phase, and here we have para-electric phase. Let's say if we consider this transition, then it's C to T, and then if we now lower the electric field, then it would be like this, and so it's just in which case the energy landscape is so electric field can lower the can modify the energy landscape, and temperature can as well. So this is two effects, and it just depends on how the electric field is going to modify it. And for this case, for example, if we consider this 100 and this 110 case, then we see that on the electric field along 100, the transition happened at a higher temperature. That means beside the temperature influence, the electric field already lower the landscape more when the electric field is in 100 direction.
Sorry, can you say it again? So what does the E dot delta P mean on the when I draw the landscape?
Okay. So E is the electric field and P is the polarization, and delta P is the polarization difference between the two transition phases. And this with and for Landau theory, if we draw the Landau and okay, let's say this is a Landau energy, and it will be a prefactor and then polarization to second order plus to fourth order plus to sixth order. They all have a prefactor, and then you will minus E electric field and P. This is a term when you want to consider electric coupling in Landau theory.
Okay.
And therefore, this is exactly the difference that the energy landscape have been reduced.
I see. Okay. And then you look at the temperature dependence. So like in one of your previous slides, you need to do this first, like at one temperature, it looks like that. And the second temperature, it looks like this. And you know, like the transition, I mean, when this and that, equals that's the
Mhm.
phase transition temperature, right? Is
That
that how I understand?
yeah, that is the transition temperature predicted by Landau theory, but in real case, we have thermal energy, so it can cross here already, and maybe even at a higher temperature. But in Landau theory, yes, that is the transition temperature.
Okay. And then now I just need to add this E dot P term. So basically, like when I expect so sometimes this one would be lower than that side. I will try to look one that is just just when two energy scale are the same, I will predict that's the transition temperature. Is that how I understand it?
I think it's like that, yeah.
Okay, I see. Okay, and sometimes E dot P is positive, sometimes it's negative. So that means sometimes the transition temperature rise, sometimes the transition temperature decrease. Is that
E dot P, yes, it can be negative and positive, depends on the direction of these two. And here, this plot, we use the delta P because we want to consider the energy between two phases. So this formula is the energy for one phase, and to consider the transition, we need to compare the energy for two phases. So here, that's why we use delta P.
I see. Okay. All right. Thank you.
Thank
I
you.
think I got it.
好，那我们先暂停录影，然后大家等一下可以继续问问题跟交流。那我们再次谢谢蓝天。
谢谢。
好。